So we have to be fluent in mathematics because a lot of times math shows up and it is used in the court of law, in the world, and people misuse it. And when you misuse it, you know, it can lead to some pretty bad outcomes. So we're going to look at a couple of those, a couple famous paradoxes, and they kind of fit in with what we're up to in this unit. So the first one I want to show you is really strange. And is a baseball example. You don't have to like baseball. I know I don't. But it kind of gets at the idea. So David Justice, this player on the left, had a better batting average in the 95 and the 96 season. So he got on base more in each of those seasons than Derek Jeter did. So if we combine the two seasons, the data from 1995 and the data from 1996, who do you think would be better? Well, in both years, David Justice had a better batting average, so you think together they'd both have, when you combine both years, of course he would have a better average. But watch what happens. Derek Jeter went 12 for 48. Well, 12 divided by 48 means that he got on a quarter of the time, so 25%. Well, David Justice went 104 from 411, so that's 253. I would rather be batting 253 than 250. Well, take 96. Derek Jeter went 183 times on base and 582 times out of 582 attempts, right? So he was batting 314. Well, David Justice was batting 321. So he beat him in 95, 96. But if you combine this data, overall, Derek Jeter batted 310 and David Justice batted 270. It's not even close. Let's take a look at a medical example. I mean, this is just baseball. Like I said, who cares? Let's talk about something real serious. Look at this lady. She's in pain. These are kidney stones. If you drink sugar pops, if you have a high sodium, high sugar diet, you don't drink too much water, you're not taking care of yourself, these guys are in your future. They're called kidney stones, right? And you have to pass them. And it's not great. It's small tube, big stone. And so there's a new treatment, and the new treatment claims that it's more effective against both small and large kidney stones. So a doctor comes in and says, well, it's better for if the kidney stone's small, and it's better if the kidney stone's large. So you'd say, well, of course I'm going to take that new treatment, right? Well, let's take a peek at it. These are the sample sizes, right? Group 1, yeah, it had a positive expectant rate of 93%, right? If it was a small stone, it worked. If it was a large stone, 73% of the time. That's better than the treatment B, right? And treatment A was better than treatment B for both the small and the large. But if you take the averages, right, combine them together, look at that, 83% of the time, treatment B is better overall. So sometimes it helps if you can narrow in the data to what if I know that I have a small kidney stone, if I know that I have a large kidney stone, to figure out which is the better. But sometimes the data gets lost. This thing is called Simpson's Paradox. And one of the most famous examples was at UC Berkeley in their admissions. They looked at each individual department and said, we know as a school, right, there's less women at UC Berkeley right now. So they started looking for bias in how they were accepting students to college. Now, we know the college admissions process is not always the most equitable thing. And so they actually got sued over it. And one of the things that they found out is they had to go each department by department. And even though that there was overall a discrepancy between the men and women that were basically in the program, when you looked at it department by department, there wasn't a discrepancy. So this was a really complex case, and kind of math and math modeling played a central role in it. I really suggest you do a little bit further reading on that. Once again, if equity is your thing, right, math is a lot of times at the center of it, right? I want to talk to you about the next thing. This is called Abrahamwalds Memo. Right? So As you can see, that's a airplane that didn't do so well. And if you look at an airplane, lots of different airplanes. These are like old fighter jets, right? Lots of different styles. You could go with a more bulky design. You could develop a plane that's bigger, it could drop more bombs, but if it's bigger, then it's slower. If you have more armor, then it's slower, but more armor, maybe, everything's kind of a trade-off, especially when you're in the, I mean, it's life or death, right? So when you're designing an airplane, you have to think critically about what is essential, what is a nice to have, to have the best outcomes. So he was born in 1902, and basically what was then the Austro-Hungarian Empire. And he was Jewish, so he had to flee Europe as Hitler rose to power. And basically he became a prominent mathematician. And in World War II, they were facing this dilemma, and he basically came up with a solution. They really respected him, and so they brought him in to kind of give them a little bit of clarity of how to go forward. The problem was, on the planes, we could add armor everywhere, but that would cost us speed, and it would also cost us money. If we didn't have to add so much armor, we could maybe build more planes. But we also need to make the pilots feel secure in what they're doing. So, like any good mathematician, he said, just give me the data. So what they did was they looked at all of the planes that came back from the war. And he said, you know what? Let's take square foot sections. So if you divide up this plane into square foot sections, so there's a square foot, there's a square foot. If you divide it up into square feet, how many bullets would we expect in each area? Like, where are our planes getting shot? And what he found was the engine in each square foot would have a little bit more than one bullet point in it, bullet hole in it. The fuselage, which is the main part of the airplane right here, 1.73. So you can see like this square foot would have 1, 2, 3 bullet holes, right? But this one. But on average, right, we talked about means in this chapter, we're almost at 2 bullet holes per section. And the fuel system is 1.5, and then the rest of the plane was 1.8. So that's everywhere that doesn't fit into those nice categories. So he thought a long time about this data, and he said, you know what? I actually know where we should put the extra armor. And it was contrary to how everyone else was thinking about it. I want you to pause the video, and if you had to choose between these 3 spots, looking at the data, what would you think would be the best spot to add that extra armor? Well, what he decided was, you know what? What we are actually studying is the airplanes that are coming back. When you're in a battle in the air, you're just kind of shooting in a random volley, right? So what we see is coming back isn't necessarily where the enemies are aiming. We're seeing what types of airplanes would come back. If there's just random shots in the fuselage, right, we could have an average of 1.73, and the plane would return. But the engine, planes are coming back, it has to be almost not hit at all. So it's kind of like the opposite of what you would think. Even though there's more bullets being, like in the return ships in the fuselage, right? The fact that there's less in the engine doesn't say that the engine's not getting shot that much. What that's really saying is if the engine shot anything more than like 1 bullet per square foot, the plane's not returning. So in this case, actually, we want to put all extra resources on the engine, which, luckily makes sense too, right? Another example from World War II where math kind of played a key role, and we're talking about distributions, right, in this chapter. Where are the distributions? How's the data organized? So these troops, they captured this tank. It's called German Panzer, right? So what they found was they took it all apart, they looked all over, and they found a serial number. And let's just say, for example, let's say they said like number 72 on the serial number. And so if they have the number 72 on it, most likely, like the chances that they only made 50 tanks and then they put 72 on this tank, like that doesn't make any sense, right? They probably were counting up and said this is like gun turret 1, 2, 3, 4, 5, 6, 7, and you just happen to capture 72. So if you want to make an estimate of how many tanks there were, how would you go about that? If you captured 72, you know probably there's more than 72 tanks coming your way, and there's probably not less than 72. But mathematically, how could you kind of model that? Well, luckily, like everything, man, math's got the answer. So let's take a look. This is their tank production based on months. There's the statistical estimate, which we'll go through in this example. And then there's intelligence reports, right? So intelligence can come from all sorts of things. Aerial photographs. It could come from, kind of spies or information people are getting from the other side. And what's kind of nice about this is we're going to actually see the true numbers. So we're going to be able to say, was the math more accurate or was the intelligence more accurate? And hint, I wouldn't be showing this if the math wasn't more accurate. Okay, so here's the first one. The first tank we get says 212. Well, like I said before, the chances that they produce 2 tanks that month and they just so happen to number it 212 doesn't make any sense, right? So most likely, and this is what this shows, this is the probability, right? So maybe there's like a 1% chance that we actually found like the highest tank number that they had. It was 212. But maybe like a 0.8% chance here, and as like, maybe we get 212 and it's out of 1,000, right? This would keep going off the grid, right? Because if we got 212, probably the chances that they made 150,000 of them, and we just happen to get this ridiculously low number tank captured, possible, but not as probable. That's why as you get over here further, it gets lower. So when we just have one piece of data, it's not very, you can't make too many decisions based on this. Well, guess what? We captured another one, and this one, it ends with 091. So now we have this blue distribution that represents, well, what if we just caught the 91st one, right? And this other blue one is, well, what if we only caught the 212? Well, now the red one says, let's put those two together. Well, since we already caught the 212, we can basically eliminate all of this data, right? And now you can see that this is a little bit sharper line with, now that we have this really low number, it drops off the likelihood that we had 1,000 or 2,000 plus tanks over here. That's going to be a really low probability. Okay, and now we get 3 more tanks. And now you can see this red, the combined probability, is really saying, you know what, most likely we're in this 250, we're in like this 250 to 300 range, right? Which makes sense given the values that we have, right? So not that many data points, but we get that final distribution after a couple more tanks are discovered. And we can make our prediction, right? Now we're pretty confident in this prediction that most of the data is going to be right in there. So this is what happened. I skipped ahead. So these were the statistics. The math modeling said that this should be it. The intelligence said this. And we can see the German records after the fact that the statistics were way closer, right? In each case. There's a couple of different things. The Germans would make fake tanks out of like, just other materials. Because if they made a whole bunch of fake tanks there, then maybe the Allied troops wouldn't go that direction. They would choose a different direction to go. And then the Germans would actually have their real tanks in that other direction. So it's a little bit of kind of trickery. There's also both sides would use audio equipment to basically project the sound of tanks moving. So people further like, oh man, I think there's tanks that way. So there's a lot of shiftiness with this in war. But basically, math is kind of the way to understand, kind of a truer representation of what's going on with the data.